Okay, a little bit of proof now. So this question here, we're being asked to prove the difference between even consecutive square numbers is always a multiple of 4. So even square numbers are things like 2 squared, which is 4, and 4 squared, which is 16, and 10 squared, which is 100. And consecutive means after each other, so if I'm going to pick 8 squared, I've also got to pick 6 squared, as those are the consecutive even numbers, 6, 8, the one after the other. And difference, you need to know, it means subtract. So we can do this numerically, and we get 64 take 36, which is something, I don't know, 18? 18? Can't be 18, 28 would be good. 28 is good. And is that a multiple of 4? Well, that is 4 times 7. Right, this is not a proof. All we've done is we've shown that it's true for one case. And this is the most common error I see marking these exam papers on this type of question, is people just do a few examples. That shows nothing. There are still infinitely many things to check doing it this way, because there are lots of square numbers, as you should know. So to check them all is impossible. You will only ever get 0% of them done. So a proof requires something that is always going to be true for all cases. So how can we write an even square number? Well, we can take what is an even number, so that's some integer, n, doubled. So that's an even number, and if I square that, that's an even square number. What's the square number, or the even square number, after that? Well, if that's the even number, the next even number is 2 after, and we can square that. And the question else talks about difference, so we're going to subtract these. So this statement here now covers all pairs of consecutive even square numbers, because I can pick any value of n and this will just be just as true. Now there are some times that will fall apart, like dividing by 0, but that won't be happening here. So now a little bit of algebra. This bracket multiplies out to 4n squared plus 8n plus 4, and this multiplies out to be 4n squared. So if you can't expand brackets, then you can't do this, but that's meant to be the easy step. All the hard work was done here, translating all of these words into this short set of symbols. If you can turn those words into those symbols, it's easy. So from here, we've just got to collect our terms. 4n squared taking 4n squared is nothing, leaving behind 8n plus 4. Now that is fully simplified. The next bit is the bit that is also a section that requires thinking. We're asked to show they're multiples of 4, so I would love to get a factor of 4 in here to show that it's there. And here there is a nice easy one, 4 lots of 2n plus 1. And because now I've got 4 lots of an integer, we are done. So, done. Okay, we're done. That's the proof. We've got 4 lots of something whole, so that's a multiple of 4. That's the entire proof algebraically. So I'll show you one where it does break. So, things to watch out for. This is a classic. If we let a equal 1 and we let b equal 1, then we know that 1 squared take 1 squared is 0. And we also know that 1 take away 1 is 0, which means we could write this algebraically. A squared take b squared is a take b. This thing on the left here factorises. We've done that recently, so that should factorise nicely to a plus b, a take b. And then we can divide both sides of this by a take b. And we've got something divided by itself. And you've learnt a rule there, that things divided by themselves are always equal to 1. And now we can remember what a and b both were. This was 1 plus 1 equals 1. So I've just shown you that 2 equals 1. Right. Hopefully you know that this last thing is garbage. You know 2 isn't 1. So I must have done something, at least one thing wrong here. So there's something different about this algebra here compared with this algebra here. This is good. This is garbage. How can you tell the difference? So, first of all, we've picked particular values for a and b at the start, which means whenever we do algebra later on, it has to be true for these values. Whereas here, we didn't pick any value for n, so this is already true for all values of n. We haven't got any values that will break it. We also, for a proof, never work on two sides of an equation. It's a different thing. This is solving an equation, relating an equation, which is slightly different from proving something. These two things are equal in size. They're not identical expressions. These two things happen to be equal in size in this special case. They are not identical expressions. So this thing at the bottom, so this isn't good technique for proof anyway. And then the thing that actually gets the falsehood out is this step, turning this into this. Something divided by itself equals 1. That isn't a rule that's always true. That has exceptions which you know, and some of you have told me yourselves. In particular, when we're dividing by something, there's a particular value we cannot divide by and stay within maths. If we ever divide by 0, the maths we've just done is no longer part of standard mathematics. It's no longer something we can use in a proof. And because a and b happen to be 1 here, this step doesn't come out true. So this step is only true if a doesn't equal b. So this equation rearranging is valid if a isn't b. But even then it's not a proof, it's just some particular arrangement of an equation. So for it to be a proof, you need to start with general cases, so n isn't defined as a particular value. You've got to work on the expression by itself step by step to end up with a thing you like. And in between, you can't do things like divide by 0 or other bad mathematical operations. If there's anything that isn't maths that goes on here, then it's no longer a valid proof. So most GCSE examples look like this. Interesting stuff, can have these kind of traps in and tricks in. So have fun with that task, and I'll see your output. Enjoy.